In the last video, we gave the definition of the semidirect product of two groups determined by some homomorphism phi. So let me just review that quickly. If H and K are groups and phi is a homomorphism from K to aught H, then we'll let G be the set of ordered pairs, something in H, something in K, where the multiplication is defined by HK times H prime K prime is H times phi K applied to H prime, comma K K prime. And we stated at the end of the video that this G with this multiplication is a group called the semidirect product of H and K determined by phi. So that's the first part of this big theorem, but there's a lot more. So the second part is about subgroups of this semidirect product. If you take the set of all things that are something in H and then the identity of K, let's call that H tilde, or the set of all things that's the identity of H and then something in K, call that K tilde. These are both subgroups of this semidirect product. The map that takes an element of H to the pair H comma identity of K, and the map that takes something in K to the pair identity in H comma K, these give isomorphisms H to H tilde and K to K tilde. Okay, so what are we saying? We're saying that inside of this semidirect product, we have a subgroup isomorphic to H, and we have a subgroup isomorphic to K. We can say more. This subgroup, H tilde, that we know is isomorphic to H, is a normal subgroup in the semidirect product. We can ask about the intersection of H tilde and K tilde, this subgroup isomorphic to H and this subgroup isomorphic to K. And this is always the trivial subgroup. This is easy to see, right? I mean, it's the only thing that's in both of these is to be in K tilde, the first coordinate must be the identity of K. But then the only element of H tilde that satisfies that is 1, 1. So we need to do something to justify that the identity of H comma the identity of K is the identity in the semidirect product, but it is. So once you see that, 4, there's nothing really to do. And then the last part of this big statement is about conjugation inside this semidirect product and how it relates to this special phi K applied to something in H that shows up in the definition of the multiplication. So let's just take something in H and something in H tilde and something in K tilde. So I really want to emphasize these are elements in the semidirect product. What happens when you conjugate something in H tilde by something in K tilde? You see that what you get is phi K applied to H and then the identity of K. So informally, if you just identify H tilde with H, this group that it's isomorphic to, and identify K tilde with K, this group that it's isomorphic to, via these isomorphisms where we'll just refer to H comma 1 as little h and 1 comma K as little k, what this is saying is that KHK inverse is phi K of H. So this is the sense in which the semidirect product is abstracting this idea of the multiplication in the product H times K involving K acting on H by conjugation, which is an action via automorphisms of H. Okay, so we're going to prove this. Let me say first, what are we saying? We've said that this semidirect product has a subgroup isomorphic to H and a subgroup isomorphic to K. And more than that, the subgroup isomorphic to H is a normal subgroup in the semidirect product. So that's what I really want to emphasize. This has a normal subgroup isomorphic to H. It has a subgroup isomorphic to K, but this subgroup K tilde is not generally a normal subgroup of the semidirect product. We'll see a little bit later in the next lecture exactly when it is a normal subgroup. but most of the time it's not. So let me just say a little last thing about this semidirect product symbol. It really does have an order to it. And one sort of nice, cute way to think about it is that the symbol is pointing towards the subgroup that you know is normal. So if you're trying to remember which way is this symbol supposed to go, it points towards the one that you know is normal. Okay, so I'm going to pause and erase, and then we'll get into the proof of why this is actually a group. You can prove this very explicitly using the definition of this multiplication operation. Let's prove that the semidirect product is actually a group. And I've written the multiplication operation up here because it's going to be really important to keep referring back to it. So hk times h prime k prime is h times phi k h prime, comma k k prime. So how do you prove that this is a group? Well, this operation really does take two things of the form something in h, comma something in k, to something in h, comma something in k, because we know phi k is an automorphism of h, so phi k h prime is definitely something in h. So okay, so this operation is well defined. Let's show that it's associative. So what do we need to show? We need to show that ax times by, in parentheses, times cz equals ax times by times cz. And I highly encourage you to watch this video, read the corresponding sections of Dummett and Foote and also Conrad's notes, and then forget about it, take out a blank sheet of paper and check that you really can follow this argument, do this argument on your own, because it forces you to practice a little bit with what does it really mean to multiply two things in a semidirect product. So let's just go one step at a time and see that this operation is associative. So what is ax times by? Well, it's a times phi x applied to b, comma xy. And we haven't multiplied by cz yet. So let's take a times phi x applied to b, comma xy, and multiply cz. Well, that's the first coordinate here, a phi x of b, times phi of this element of k, phi xy, applied to the first element here, c, comma xy times z. Okay, well, what is that? This is a part where it's helpful to really think about what's going on. We know that we have this homomorphism from k to aught h. So what is phi of x times y? It's the automorphism phi x following the automorphism phi y. So the left-hand side here, this is a times phi x of b, and then phi x of phi y of c. And now on the second component, all I want to do is move the parentheses by the associativity in k. So if you're going to find this argument for associativity confusing, I would think that this piece is really where you need to think about a little bit what's really going on here. Okay, and now the rest of it, well, what is this? This is a of phi x of b is some element in h. Phi x of, well, let me say it this way. B is some element of h. Phi y of c is some element of h. Phi x applied to a product is the same as phi x applied to the first thing times phi x applied to the second thing. So this is a times phi x of b times phi y of c. So this is a product of two things in h, and then we haven't changed anything over here. And now this is a times x, or a comma x, times b times phi y of c, comma yz. This is another sort of key step. Really convince yourself that you think that this is true. And this, now we can see, is a comma x times this product is, or this element is b comma y times c comma z. Okay, so the only thing that we're doing here is working directly with the definition of what it means to have this homomorphism phi from K to aught H, but it's really worth going through it carefully. All right, so now we have this associative binary operation on this set of pairs H comma K. I claim that 1, 1 is the identity. Identity of H comma identity of K. So what is 1, 1 times HK? Well, it's 1 times phi1 applied to H. So this is the, this 1 is the identity in K. This 1 is the identity of H. But, and then, 1 times K, which is just K. What is phi1? Well, it must be the identity permutation of H. So we get 1 times H, which is just HK. Okay, but to check that it's an identity, we really want to check that 1, 1 times HK is HK, and HK times 1, 1 is also HK. And here, the product looks different. We get H times phi K of 1, comma K1, but phi K is an automorphism of H, so it definitely sends the identity to the identity. So we get H times the identity of H, comma K1, so we get HK. So this really is the identity. Now we just need to see that every element H comma K has an inverse that is something in H comma something in K. And I need more space to do this calculation, so I'll just say for now, my claim is that the inverse of H comma K is phi of K inverse applied to H inverse, comma K inverse. So how do you remember what this formula is? Well, it looks just like this star star from earlier when we talked about the case where H and K are subgroups inside a common group G where H is normal in G. So in that case, we had this product set H times K. And what was the inverse of H times K? It was K inverse H inverse K times K inverse. So this looks really, really similar if you just put commas in between the element of H and the element of K. So H comma K, K inverse H inverse K, comma K inverse. Right? So that looks just like phi K inverse of H inverse when the action of K on H is conjugation. Okay, so I'll pause and erase, and then I will show you that this element really does satisfy the things that an inverse needs to satisfy. Let's finish this proof that our semidirect product actually is a group by checking that this formula I wrote down for the inverse of the element HK really does satisfy the things that you need to be a two-sided inverse. So let's just check what is HK times phi of K inverse of H inverse comma K inverse. Well, it's H times phi K applied to this element. So phi K of phi K inverse applied to H inverse, comma K inverse. Okay, but what is phi K of phi K inverse of something? That's phi of K times K inverse of that same thing. So we get H of phi K inverse applied to H inverse, comma 1. And phi of K inverse is phi of 1. It's the automorphism of H corresponding to the identity element of K. So that's just the identity map on H. So we get H times the identity applied to H inverse is just H inverse. So we get H inverse 1, which is 1, 1, which is the identity. So let's check that the inverse property works when you multiply in the other order. Phi K inverse of H inverse, comma K inverse times HK. That's phi K inverse of H inverse times phi of K inverse applied to H, comma K inverse times K. But what is this? Well, because phi K inverse is an automorphism, in particular, it's a homomorphism from H to H. So phi of K inverse of something times phi of K inverse of something else is phi of K inverse of the product. So we get phi K inverse of H inverse times H, comma, the identity of K. And this is phi K inverse applied to the identity of H. But because phi K inverse is an automorphism, it sends the identity to the identity. So this is phi k inverse of 1, comma 1, which is 1, 1. So we've seen that this formula really does give the inverse of the element hk. And now we have a set with an associative binary operation that has an identity and where every element has an inverse. So this semi-direct product of h and k with respect to phi really is a group. Okay, I'm going to pause and erase, and then we'll prove those remaining pieces of the big theorem about semi-direct products. This was the sort of like long part. Everything else will be pretty straightforward. We've now seen that the semi-direct product of h and k with respect to phi is a group. So let's prove the other parts of this main theorem about semi-direct products. The first was that h tilde, the set of things that are something in h comma the identity of k, and k tilde, something or which is the identity of h comma something in k, that these are both subgroups of the semi-direct product. I'm not going to do all the details here. The easiest thing to do is just see what happens when you multiply two of these elements. So h1 times h prime 1 is h times phi of 1 applied to h prime, comma 1 times 1. So that's h, and then phi of 1 is the identity permutation. So we get h prime 1. Very, very similar. 1k times 1k prime is 1 times phi of k applied to 1, comma kk prime, which is 1 kk prime. So in this way, we're seeing that when we multiply two elements in h tilde, it's just like multiplying two elements in h. If we multiply two elements in k tilde, it's just like multiplying two elements in k. So I'll leave the rest of the proof that these actually are subgroups for you to fill in. Okay, how do we see that these subgroups are isomorphic to h and k respectively? Well, this is also very straightforward given what we've seen. The map that takes some element little h in h to the pair h comma 1 in h tilde, this is an isomorphism. And the same thing, the map that takes some element little k in k to the pair 1 comma k, this is also an isomorphism. This is very easy to check given how the product works in h tilde and k tilde. So I won't write out the details here. When we stated the theorem, we said that this statement that h tilde intersects k tilde was just 1, 1, the trivial subgroup of the semi-direct product. That's easy to see once you just look at how h tilde and k tilde are defined. I just want to emphasize that now we know 1 comma 1 really is the identity in this group. So what's left to prove is there was this statement 5 that was what happens when you conjugate an element of h tilde by something in k tilde. And we can just multiply it out. 1k times h1 times 1k inverse. Sorry, this should be 1k inverse is 1k times h1 times 1 comma k inverse, right? Because the inverse of the element 1 comma k is 1 comma k inverse. I mean, you can think about it this way, or you can use that formula for inverses that we just talked about before. All right, so let's multiply the first two terms and then multiply by the third one at the end. We get 1 times phi k applied to h, comma, k times 1, which is just k. We now multiply by 1 times k inverse. So this is phi k of h times phi k applied to 1, and then k inverse. And this is just phi k of h, comma 1, which is the formula that we were trying to prove. Okay, so we've seen how conjugating an element h by an element of h tilde by an element of k tilde leads naturally to this phi k of h. All right, so what's the last thing that we have to prove from this big statement is that h tilde is a normal subgroup of the semidirect product. So we'll show that it's normal by showing that its normalizer is the entire semidirect product. And clearly h tilde is contained in the normalizer. So we're going to show that this subgroup is normal by showing that the normalizer is the whole group, by showing that k tilde is also a subgroup of the normalizer. So, I mean, how do you see that? you see that from this formula we just wrote down. But I'll pause and erase and write out the details more carefully and also explain why this is enough. Let's finish the proof that H tilde is a normal subgroup of the semidirect product. So first, let's note that every element of the semidirect product can be written as something in H tilde times something in K tilde. Why is that? Well, H1 times 1K is H times phi1 applied to 1, which is just the identity, comma, 1 times K. So H times 1 times K is just HK. So any element HK can be written as something in H tilde times something in K tilde. So what does that mean? The product set H tilde K tilde is the whole semidirect product. So if you have these two subgroups inside the normalizer of H tilde, which we know is a subgroup of the semidirect product, and these two subgroups together, their product set is the whole group, then that means that the normalizer of H tilde is the whole group, which means that H tilde is normal in this semidirect product. Okay, so we just have to show that K tilde is contained in this normalizer, but we just saw what happens. I mean, we just saw it like right here, that when you conjugate an element of H tilde by an element of K tilde, you get something that's still in H tilde. You get phi K applied to H, comma 1. So that means that K tilde is contained in the normalizer. So by this argument right here, we've seen that H tilde is a normal subgroup in the semidirect product. So we know K tilde is a subgroup. In the next lecture, we will see exactly the conditions under which K tilde is also a normal subgroup, but it usually is not.